Why was hybridization theory developed? Why is this theory so important? And how does it allow the chemist to envision a molecule in 3 dimensions? In this chapter, we will explore some of the reasons why hybridization theory was developed. A student's ability to take a 2-dimensional molecule off the blackboard during lecture and fold it into 3 dimensions, or envision a molecule in 3 dimensions from a page in a book, is arguably one of the most essential skills when learning chemistry. The chemistry student who has the ability to visualize molecules in 3 dimensions is rewarded with a better understanding of chemical properties, physical properties, and most importantly, the ability to predict chemical reactivity. Understanding how atoms within molecules are oriented in 3 dimensions requires an understanding of hybridization theory. From simple molecules such as ethanol to more complex molecules such as the highly toxic tetrodotoxin, the concepts of hybridization are the foundation to our understanding of molecular geometry. However, looking at a 2-dimensional Lewis structure of a molecule affords much information to the scientist. For example, the overall connection of atoms within the molecular formula. After all, different structural and geometric isomers can be imagined from relatively simple molecular formulas. To introduce the concepts of hybridization, we will first focus all of our examples on the carbon atom. The basic principles discussed for the carbon atom can also be applied to other elements, which are explored in later sections. A carbon atom has 6 electrons in the following configuration: 1s2, 2s2, 2p2. The relative energy electron configuration diagram is another way to visualize where the electrons are located. Each arrow in this diagram represents one of the individual electrons of carbon. However, only the valence or outermost electrons are responsible for bond making and bond breaking. Thus, we can ignore the inert noble core electrons, which we can represent here as the helium element. This abbreviated electron configuration quickly allows one to ascertain that there are 4 valence electrons. It would appear that there are only 2 unpaired valence electrons capable of forming covalent bonds, one in the 2px and one in the 2py orbital. However, it is well known that carbon forms a total of 4 covalent bonds to attain full valency. Thus, all 4 valence electrons must be involved in bonding. Hybridization theory was developed in order to better explain the 4 observed bonds of carbon. In addition, the hybrid model best explains overall molecular geometry of carbon. In other words, bond angles in 3 dimensions can be predicted. The possible hybrid combinations for a carbon atom are sp3, sp2, and sp, and are explained in detail in subsequent sections. Let us first start by examining the shapes of the atomic orbitals for carbon. The 2s atomic orbital is a sphere, and the 3 2p atomic orbitals are shaped like dumbbells, oriented along the 3 axes, 2px, 2py, and 2pz. Think of these 4 atomic orbitals as 3-dimensional shapes, where you are most likely to find an electron 90% of the time. Notice that the electrons have access to both lobes for the 2p orbitals. Starting from the abbreviated electron configuration for carbon, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Although we now have 4 unpaired electrons for bonding, we still can't explain the experimentally observed bond angles for a tetravalent carbon. Thus, when we mix the 2s atomic orbital with all 3 2p atomic orbitals, we create 4 new degenerate energy hybrid orbitals. The shape of the new sp3 hybrid orbital is best characterized as 1 part s and 3 parts p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes, where you can find the electron 90% of the time. The hybridized carbon now possesses 4 unpaired valence electrons and is said to be an sp3 hybridized carbon. When we superimpose all 4 sp3 hybrid orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. The 4 new hybrid orbitals attempt to get as far apart from each other as possible, 109.5 degrees. Think of this as the orbitals attempting to minimize repulsions between them. Thus, they are oriented towards the corners of a tetrahedron with all angles at 109.5 degrees. Your instructor will often draw the sp3 hybridized carbon on the blackboard as shown. The 2 solid lines in this drawing are in the plane of the board. The wedge represents the electron coming out of the plane of the board, and the dashed line represents the electron going back behind the plane of the board. Each of the 4 sp3 hybrid orbitals contains 1 electron capable of forming a covalent bond. The sp3 hybridized carbon is now capable of forming 4 covalent bonds. Here, X represents any atom with a valence electron capable of forming a covalent bond. Because the electron density is symmetrically located about an imaginary line that runs through the 2 adjacent nuclei, we call these bonds sigma bonds. An example of a simple carbon compound with an sp3 hybridized carbon is methane, CH4. The ideal bond angles are all 109.5 degrees, due to all 4 equal in size hydrogen atoms attempting to get as far away from each other as possible. Your instructor will often draw methane on the blackboard as shown. Again, the 2 solid lines in this drawing are in the plane of the board. The wedge represents one of the hydrogens coming out of the plane of the board, and the dashed line represents one of the hydrogens going back behind the plane of the board. Another simple carbon compound that utilizes sp3 carbons is ethane. From the 2-dimensional Lewis diagram, we see that each carbon has 4 single bonds. Thus, both carbons are sp3 hybridized. Starting with 2 sp3 hybridized building blocks, we can start to construct the molecule in 3 dimensions by forming the CC sigma bond. Next, the 6 hydrogen sigma bonds are formed, which affords the final 3-dimensional structure for ethane. The 2-dimensional Lewis diagram for ethane implies that all 4 bond angles are 90 degrees. However, employing the basic principles of hybridization theory, we see that the bond angles are all nearly 109.5 degrees. Now that the molecular geometry for ethane in 3 dimensions has been determined, we can begin to examine some of ethane's interesting physical properties. For example, free rotation may occur about the carbon-carbon single bond, which allows us to explore simple conformational analysis. Conformations are different arrangements of atoms due to these rotations. When we place the electron density around each hydrogen atom, we see that the hydrogen atoms from adjacent carbons do not touch. To make this diagram easier to view, we will remove the electron density from 2 of the hydrogen atoms from the back carbon. Even though the hydrogen atoms from adjacent carbons do not touch, there is torsional strain due to the electron clouds of the adjacent carbon-hydrogen bonds, which impedes the rotation about the CC bond. This gives rise to the staggered and eclipse conformations for ethane. The difference in relative energy between these 2 conformations is approximately 3 kilocalories per mole. It may be easier to remember that atoms want to be as far apart from each other as possible. Think of it as less crowding. When molecules are viewed down the CC sigma bond, we call this a Newman projection. Often you may see your instructor represent the Newman projection on the blackboard as follows. When we replace one of the hydrogen atoms with an atom that has a larger atomic radius than hydrogen, steric factors will arise, which will increase the barrier of rotation. As the dihedral angle changes, so does the relative stability of the molecule. Similar to the first step of sp3 hybridization, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital with 2 of the 2p atomic orbitals creates 3 new degenerate energy hybrid orbitals. The shape of the new sp2 hybrid orbital is best characterized as 1 part s and 2 parts p. As with all orbitals, think of these hybrid orbitals as 3-dimensional shapes where you can find the electron 90% of the time. The sp2 hybridized carbon now possesses 3 electrons in hybrid orbitals and 1 electron in an unhybridized 2pz orbital. When we superimpose all 3 sp2 hybrid orbitals with the unhybridized 2pz orbital onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density of the unhybridized p orbital is shrunk to 1/3 of its size for simpler viewing. The 3 new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the hybrid orbitals attempting to minimize electron repulsion. Thus, they are oriented 120 degrees apart. Your instructor will often draw the sp2 hybridized carbon on the blackboard as shown. Again, remember that solid lines are in the plane of the board, wedges are coming out of the plane of the board, and dashed lines are going back behind the plane of the board. Before we begin to show how the sp2 hybrid building block takes part in bonding, it is important to remember that the electron in the unhybridized 2p orbital has excess to both lobes. Each of the 3 sp2 hybrid orbitals contains 1 electron capable of forming a sigma bond. Thus, the sp2 hybridized carbon is now capable of forming 3 sigma bonds and 1 pi bond. A simple carbon compound that utilizes sp2 carbons is ethylene. From the 2-dimensional Lewis diagram, we see that each carbon forms 3 sigma bonds and 1 pi bond. Thus, both carbons are sp2 hybridized. Starting with 2 sp2 hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the cc sigma bond. Next, the 4 carbon-hydrogen sigma bonds are formed, which affords the planar sigma bond framework for ethylene. To form the second bond between the carbons, called the pi bond, we can imagine that the 2 adjacent parallel unhybridized 2pz atomic orbitals overlap. When they overlap, the 2 electrons can be shared, allowing each carbon to attain full valency. The 2-dimensional Lewis diagram for ethylene allows the chemist to view the gross connectivity of the atoms. However, no information is conveyed about the pi bond. When the molecule is represented in 3 dimensions, we see that half of the pi bond is above the plane and the other half of the pi bond is below the plane. An understanding of this electron density within a pi bond will become very useful when predicting reactivity of alkenes. To gain a better understanding of the pi bond, we should recall the actual shape of the unhybridized p orbitals. When we envision the actual shape of these orbitals, overlap between the adjacent p orbitals is possible, which allows for the sharing of these two electrons. However, it is very difficult to draw the molecule this way. Thus, you will often see the pi bond represented in its abbreviated form on the right. Understanding the pi bond helps us realize why geometric isomers are isolable. Geometric isomers have the same gross connectivity, but differ only in how the groups are oriented in space due to hindered rotation about the doubly bonded carbons. When we draw an imaginary line along the axis of the double bond, and then compare groups on each carbon using the Kahn-Ingold-Prelog sequence rules, we can determine if the groups of priority are on the same side, called the cis isomer, often abbreviated Z. Alternatively, the groups of priority can be on opposite sides of the imaginary line called the trans isomer, often abbreviated E. For interconversion of the isomers to occur, we need to have free rotation about the carbon-carbon double bond. If this were to happen, it would mean that the pi bond would have to break, which requires approximately 70 kilocalories per mole. This will cause each carbon to lose full valency due to the two p orbitals no longer overlapping, which will make the alkene unstable or higher in relative energy. Thus, at room temperature, geometric isomers are isolable. Similar to the first step of sp3 and sp2 hybridization, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital with one of the 2p atomic orbitals causes two new degenerate energy hybrid orbitals. The shape of the new sp hybrid orbital is best characterized as 1 part s and 1 part p. As with all orbitals, think of these hybrid orbitals as three-dimensional shapes where you can find the electron 90% of the time. The sp hybridized carbon now possesses 2 electrons in hybrid orbitals and 2 electrons in the unhybridized 2p orbitals. When we superimpose both sp hybrid orbitals with the unhybridized 2pz and 2py orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density of the unhybridized p orbitals is shrunk to 1/3 of their size for simpler viewing. The 2 new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the orbitals attempting to minimize electron repulsions. Thus, they are oriented 180 degrees apart. Before we begin to show how the sp hybrid building block takes part in bonding, it is important to remember that the electrons in the unhybridized 2p orbitals have access to both lobes. Your instructor will often draw the sp hybridized carbon on the blackboard as shown. Again, solid lines are in the plane of the board, shaded lobes are coming out of the plane of the board, and dashed lines are going behind the plane of the board. Each of the 2 sp hybrid orbitals contains 1 electron capable of forming a sigma bond. The sp hybridized carbon is now capable of forming 2 sigma bonds and 2 pi bonds. A simple carbon compound that utilizes sp carbons is ethyne or acetylene. From the two-dimensional Lewis diagram, we see that each carbon forms 2 sigma bonds and 2 pi bonds. Thus, both carbons are sp hybridized. Starting with 2 sp hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the Cc sigma bond. Next, the 2 carbon-hydrogen sigma bonds are formed, which affords the linear sigma bond framework for ethyne. To form the second and third bonds between the carbons, called the pi bonds, we can imagine that the 2 pairs of adjacent parallel unhybridized 2p atomic orbitals overlap. When they overlap, the 4 electrons can be shared, allowing each carbon to attain full valency. The two-dimensional Lewis diagram for ethyne allows the chemist to view the gross connectivity of the atoms. However, no information is conveyed about the pi bonds. When a molecule is represented in 3 dimensions, we see that half of each pi bond is above and below a plane. An understanding of this electron density within these 2 pi bonds will become very useful when predicting reactivities of alkynes. To gain a better understanding of the 2 pi bonds, we should recall the actual shape of the unhybridized 2p orbitals. When we envision the actual shape of these orbitals, overlap between the adjacent 2p orbitals is possible, which allows for the sharing of these 4 electrons. However, it is very difficult to draw the molecule this way, thus you will often see the pi bonds represented in the abbreviated form on the right. An easy way to deduce hybridizations is to count groups around a central atom. A group is defined as another atom or a lone pair. When an atom is surrounded by 4, 3, or 2 groups, it will adopt the sp3, sp2, or sp hybridizations, respectively. A helpful way to remember this is by adding the exponents together. That should equal the number of groups around the hybridized atom. For sp3, the exponents add to 4. Thus, an sp3 atom has 4 groups. For sp2, the exponents add to 3. Thus, an sp2 hybridized atom has 3 groups around it. These hybridizations allow the respective number of groups to be as far apart as possible. Again, think of it as all groups attempting to minimize electron repulsion. Although we will use the abbreviated hybridized building block shown here for subsequent examples, it is important to recall the actual shape of the unhybridized and hybridized lobes on carbon. For example, the unhybridized lobes were shrunk to 1/3 of their size, and we simply showed how the electrons in the hybrid orbitals were oriented in 3 dimensions, so that the carbon building block does not become too cumbersome and confusing. A simple carbon compound that utilizes both sp3 and sp2 carbons is propylene. From the two-dimensional Lewis diagram, we see that by counting groups, we can deduce the hybridization for each carbon atom. 4 groups employ the sp3 hybridized building block, and 3 groups employ the sp2 hybridized building block. Starting with 1 sp3 and 2 sp2 hybridized building blocks, we can start to build the molecule in 3 dimensions by forming the carbon-carbon sigma framework. Next, the 6 carbon-hydrogen sigma bonds are formed, followed by the pi bond, affording the final 3-dimensional molecule. Notice that the methyl group can freely rotate about the carbon-carbon sigma bond, while the pi bond affords no rotation. Within acetamide are central atoms that we have not dealt with yet, nitrogen and oxygen. However, we employ the same concept for deducing hybridization. Simply count groups on these atoms. which means we also have to count the lone pairs as groups. 4 groups around nitrogen and 4 groups around carbon allows us to deduce sp3 hybridization, while 3 groups around the oxygen and carbonyl carbon allows us to employ sp2 hybridized building blocks. Once all the hybrid building blocks have been deduced, we assemble the sigma bond framework, attach the hydrogen atoms, and form the double bonds as shown. Again, we see that the CH3 group can spin freely about the carbon-carbon sigma bond, while the pi bond affords no rotation. In addition, the NH2 group can spin freely about the carbon-nitrogen sigma bond. Now let's look at a compound that utilizes an sp hybrid building block, carbon dioxide. Again, from the two-dimensional Lewis diagram, we see that by counting groups, we can deduce the hybridization for each atom. 2 groups employ the sp hybridized building block, and 3 groups employ the sp2 hybridized building block for both oxygen atoms. Starting with one sp and sp2 hybridized building blocks, we can start to construct the molecule in 3 dimensions by forming both CO sigma bonds. For both pi bonds to form, we need to rotate the oxygen on the right forward so that the adjacent unhybridized 2p orbitals are parallel. Thus, both pi bonds form, affording the final 3-dimensional molecule. Notice that the 2 pi bonds are perpendicular to each other. In addition, the lone pairs on each oxygen atom are perpendicular to each other. As you become comfortable with the concepts of hybridization, you will be able to fold 2-dimensional Lewis structures into 3 dimensions in your mind. With practice, you will also be able to allow the molecule to undergo conformational changes in your mind while predicting the more stable conformer due to steric interactions and other effects. Here we see that the methyl group prefers to be in the equatorial position. Thus, one of the chair conformations is favored over the other. As we have seen, ideal bond angles are obtained from the hybrid building blocks. However, deviations from ideal bond angles can and do occur in virtually all molecules when groups are not equivalent. For example, the sp3 hybridized oxygen of water has a lone pair interaction, which will cause the 2 hydrogens to become closer than their ideal bond angle of 109.5 degrees, about 104 degrees. VSEPR, valence shell electron pair repulsion theory, allows the chemist to make predictions regarding deviations from ideal bond angles. A general trend that allows predictions from ideal bond angles is lone pair interactions are greater than lone pair bonding pair interactions, which are greater than bonding pair interactions. The sp3 hybridized nitrogen within the ammonia molecule has 3 lone pair bonding pair interactions, which will cause the 3 hydrogen atoms to become closer than their ideal bond angle of 109.5 degrees, about 106 degrees. An interesting property of nitrogen is that it has the ability to undergo inversion of configuration, demonstrating that hybridizations can transform. For this umbrella-like effect to happen, we see that the nitrogen hybridization appears to change from sp3 to an sp2 like nitrogen, and back to sp3. Current theories predict that there are 200 billion inversions per second for a molecule of ammonia. If chemistry is considered to be the central science, then hybridization theory may be considered the cornerstone of chemistry. After all, the student who has the ability to visualize molecules in 3 dimensions is rewarded with a better understanding of chemical properties, physical properties,